Great.
All right, excellent. Thank you.
Okay, thanks for coming, everybody. We are super excited to have Francis here today as our speaker. Francis Hellman is a professor at the University of California, Berkeley in the departments of physics and material science and engineering, as well as a senior faculty staff scientist in the material sciences division of Lawrence Berkeley National Lab. She served previously as physics department chair and more recently as dean of the division of mathematical and physical sciences in the College of Letters and Sciences, while continuing to be actively engaged in research and teaching, and served as president of the American Physical Society, or APS. She has over 250 publications and 4 patents, and has supervised the research of many undergraduate and graduate students. Professor Hellman is a world-leading expert in thin film growth and nanocalorimetry measurements, particularly of vapor deposited thin amorphous films, both magnetic and non-magnetic. She and her research group developed micro and micro-based microcalorimeters capable of operating in extreme environments with unprecedented sensitivity and accuracy. She is a recognized leader in magnetic materials, particularly in advancing the understanding of the importance of interfaces and spin-orbit coupling for amorphous materials, and deepening our understanding of their magnetic and thermodynamic properties, and was invited to be a member of LIGO, the Gravitational Wave Observatory, in recognition of her contributions to understanding low-loss optical coating materials. Dr. Hellman is an elected member of the American Academy of Arts and Sciences in 2013, and an elected fellow of the APS since 1997. She's strongly engaged in scientific public outreach, including being a visiting scientist at the San Francisco Exploratorium, and she is deeply committed to educational activities that help increase diversity in science. She holds a doctorate in applied physics from Stanford University and a bachelor's degree in physics from Dartmouth College. She was a postdoc at AT&T Bell Labs, followed by appointment and many years as professor at UC San Diego, and came to UC Berkeley in 2004. And she's also my advisor, so I'm especially excited to have her here today. So please join me in welcoming Francis Hellman.
Cool, thanks. So, yeah, thank you. That was a lovely introduction. I guess I must have written that at some point, but anyway, so I'm here today. I am what you've had talks from a whole variety of fields, I imagine. I'm what's called a condensed matter physicist. Sometimes call myself a materials physicist, which means that I work on the understanding the properties of solid materials. And by properties, I mainly mean electronic, but not entirely. There's sort of a way in which in the last 10 years, I've gotten increasingly involved in what is going to be a lot about today's talk, which is about these non-crystalline materials. And there's a way in which I'm still interested in their electronic properties, but I'm also interested in their structural properties, and in this kind of well, amazing state, which underpins the hidden beauty statement, that most people, I'm going to explain to you carefully what an amorphous or non-crystalline material is, but most people, the simplest explanation is you take a liquid and quench it really fast, and in some materials they don't crystallize. You can just quench them and they stay in what many people call the like a snapshot of the liquid state. And you actually all know pretty well, and the most obvious example of this, which is window glass. So how many of you have ever seen glass blowing, or at least are aware of glass blowing? Okay, almost everyone. Well, think about what you've seen when you see glass blowing. You take a blob of, not quite, I mean, if it's really a liquid, it won't stay on the end of the stick. So you have to take a glob of something that is pretty darn gooey and thick, but not solid. So, and then you blow in a tube and you make, bubble, you make shapes, you make bowls, and you make whatever shapes you've seen. Chihuly makes these amazing sculptures out of this. But that critically depends on the fact that that material, it's not a liquid and it's not a solid, and it's somewhere halfway in between. But most things you learn about in your classes, there is no such thing as halfway in between. There's liquids, there are solids. You talk about freezing of water and it turns into ice, things like that. So most things don't have a halfway in between. And the halfway in between is the only reason you can do that glass blowing. Like if you take a glass of water, of course you can blow bubbles into it, but they go away as soon, blow a bubble and then it goes away. If you freeze it, you can't blow a bubble at all. So you do need this thing called a glass transition where it starts off as a liquid and then you let it cool a little bit and it gets thicker and more viscous. And at about the moment you have to get the right viscosity. It has to be gooey enough that you can make a shape with it and have it hold its shape and then continue cooling it. And that's called the glass transition. And those are called glassets. So that's what I'm referring to there as liquid quenching. So how fast you quench matters. And without that property, like window glass is that. If there is also, so window glass is mostly SiO2, silicon dioxide. You can also get crystalline SiO2, and that's called quartz. And you may have even heard, like you get, quartz, some of the fancy wine goblets you get and things like that are actually crystal quartz. The thing about crystal quartz is it's brittle, much more so than window glass. But and also if you get a quartz water glass or something like that will be very expensive compared to a glass. I shouldn't have used the glass price. A quartz goblet, let's call it, like the thing you want to drink from. That will easily be $50, $100, something like that. Whereas just a plain old drinking glass is like $1. So this process of being able to make glasses, meaning glass, that's where the word comes from, is really important to technology. And so a lot of work goes into it. It isn't really just SiO2. They put a bunch of other stuff in there to help it with its strength, to help it with how it cools, where it freezes, things like that. So that is what's traditionally known as glasses. It has turned out in sort of the last century, so it's a while this has been known, that there are other ways of getting to the same structure. And that other way is the technique that we use in my lab. So you can do vapor deposition, where you have a big, like a bell jar, a vacuum chamber, and you evaporate material. So you could evaporate, instead of liquid SiO2 that you then quench, you could evaporate SiO2, have the molecules of SiO2 land on a substrate, and freeze there and become solid. So for a long time, one of the underlying questions is it the same stuff? You didn't get there by the same route, but is it nonetheless the same stuff? Now you have to ask what you mean by the same stuff. What you really mean is the same properties. You would not want to make windows by this technique. You sort of are doing it not quite an atom at a time, but a layer at a time, and it would be really slow. So you don't. That's not how you make window glass. But a lot of materials you can make really good. The term was developed of amorphous materials. And there are some purists in the field who still try and draw that distinction. Like a glass has to be liquid quenched. And anything that is not liquid quenched, we're going to call amorphous. To my eyes, that is a distinction without any meaning. They're not different materials. I can make better materials. I can make worse materials. There's lots of things I can do. There are things about vapor deposition that are pretty specific, but by and large, you're making the same material. So I do not hold on to that distinction. So I will just from henceforth call everything amorphous. And one of the underlying questions is, well, is the structure really just the same as if I took a snapshot, imagine taking a photograph, if you will, of something where you caught an image of exactly where every atom was. Is that the same structure? And I'm going to argue to you that it's not. There's a way in which that is a pretty highly disordered. The liquid is quite highly disordered and it's sloshing around, but it is pretty disordered compared to the materials that we make by vapor deposition. They actually have quite a bit of order in them. Now it's mostly local order. So let's talk a little bit about what I mean by local order. I've already told you about SiO2. So if I mix together silicon and oxygen, pretty much every silicon atom in there is going to be bonded to two oxygens. That's the way the electrons like to, that's what they want to do, so they will. And, an oxygen atom and a silicon atom, they will move around such that every silicon will be bonded to an O2, to two O's. In a particular bond angle, there is actually a characteristic oxygen, Si, oxygen, like H2O. So I imagine you've seen pictures of the H2O molecule. It also has a sort of an asymmetric shape to it. It's not like a straight line. It has a shape, and so does SiO2. So that is the short range order. Then you have to ask, how do they bond to each other? So imagine I have here an SiO2, well, I don't really want, I guess I just want that. So there's my Si molecule there, and there's my two O's. So how is this guy going to connect? Well, you're going to end up sharing an oxygen, and that angle, it turns out, is pretty floppy. So that is where the disorder in SiO2 happens. It is not in that angle, it's in this other angle. And that is a lot of disorder. And so that's a good example of something you might need to understand if you want to make good SiO2. SiO2 is an interesting one because even I said the crystal as though there was one crystal, but that's not true. I mean, SiO2 comes in a bunch of crystal structures. Almost everything, we'll mostly stick to single elements here, but an example that is important in everyday life, which is iron. So iron is magnetic, and that's important for a lot of technologies. And iron is magnetic, and it forms in what's called the body-centered cubic structure, which is like a cube with an atom at the middle. And that is important to its properties. It can also form in what's called a face-centered cubic structure, which is a cube, but now instead of one at the middle, I have one at each face. Face-centered cubic leads to a lot of different magnetic properties. So it is very possible for a single element to have more than one crystal structure it can form in. You could then ask the question of what's the ground state? Well, the ground state, meaning the lowest energy state, so the temperature equals zero, the temperature equals zero state of iron is that BCC structure, magnetic BCC, that's the ground state. So one can then ask the question, well, how much higher energy is the FCC state? And it is a bit higher in energy. That's why it's not the ground state. So at T equals zero, there's only one ground state, but there is another state, and it is possible to make it in that other state, the FCC state. And if you do that, you can trap it. We call that a metastable state. So there can be lots of these. There's a lot of crystal structures out there, and even if I just have one element, there's a lot of different materials you can make with that one element. And it turns out that, so FCC iron has very different magnetic properties than BCC. So this matters. I'm going to give you an even better example. This is going to be important in a moment to my amorphous arguments as well. But let me give you another example that you have already known about, whether you've thought about it or not, which is carbon. Okay, so carbon, there are two forms that carbon likes to form in, and one of them is graphite, which is pencil lead. So graphite is this very layered structure. Some of you may have even heard of graphene, which is a single layer of graphite, but I'm not, that isn't really a different structure. That is just a single layer of graphite. Important, but let me not dwell on that one. So just graphene has this very, very layered structure, and it's very soft. That's why I can write with that. The other form of carbon is diamond. Really is about as different as you could possibly get. So diamond is actually diamond, the thing that is the hardest structure, the hardest single element that we know about. It is literally the thing, diamond rings, et cetera, et cetera. And there's there's a line, at least in a Bond movie, about how diamonds are forever. Well, that's an interesting statement because diamond is not the ground state. Graphite is the ground state. So at T equals zero, the ground state of carbon is graphite. Okay, so most people don't realize that. And that most people don't realize that because if you manage to make diamond, it does seem to last forever, like beyond the lifetime of the universe. So that's the thing to keep in mind is you don't necessarily get to the ground state. You can be in so diamond is actually a metastable state. It's a higher energy than graphite. But if you make it, you will not get there in the lifetime of the universe unless you heat it up. So how do you make diamonds? Probably you mostly know how you make diamond. Diamond is the ground state under high pressure. So if I take graphite or even just disordered amorphous carbon and put it under pressure, so diamond is a much denser structure than graphite. In graphite, there's a lot of empty space. Diamond is a very close packed thing. So it kind of makes sense if you squash graphite at some point at high pressure, the ground state will become diamond. Now, even then, it won't happen unless you heat it up. So the way you actually make diamond, you have to apply high pressure and lots of temperature, lots of heat. And then it will transform into diamond. Then you release the pressure and the temp, and you cool it down. And now it's in a diamond state where it'll stay forever. Does that make sense to everybody? It's just a little unexpected, but it is, it is true. Now, those two, if you look at the atomic level, those two structures have really different, they have the same atoms. I mean, the atom hasn't changed at all. This is not about isotopes. I mean, there are also isotopes. Carbon comes in a bunch of, carbon 12, carbon 13, et cetera, with different neutrons. But none of this is about the neutrons. Solid state physics and chemistry more generally is all about the electrons. The nucleus only matters in the sense that that tells you how many electrons there are. So all of chemical bonding is all about the electrons interacting with each other and feeling the positive ion cores matters, but it's not really about the nuclei. So, the diamond, starting with the diamond has it's column 4. So each carbon atom has 4 electrons on it. So those 4 electrons, each carbon wants to bond to 4 carbons, each of them contributing 1 electron. So carbon likes to make what we call the diamond structure, that is the parent compound. And that is like this tetrahedron, where every carbon is bonded to exactly 4 other carbons. And if you think about it, I actually have a picture in a moment where I'm going to show you the same structure in silicon. In fact, let me just jump to that and then I'll come back to where I am right now. Okay, so that here on the left, that is actually silicon, which is what I'm going to talk a lot more about in a second. But that is the diamond structure. And you can see, if you look at it for a second, I don't have pointers.
So make a pointer on the podium behind you.
Oh, yes, sure. And figure out which end is which. I almost pointed away from me, and here's a back of it, so let's see, let's start. All right, I'm just going to point this. Oh, you got it. This is going to do it right there. Boom, got it. Thank you. He's a really excellent student in the lab, by the way, in case that wasn't obvious. So, okay, so this is the diamond structure. And if you just pick any of these, pick one of the ones in the middle so it has all its neighbors, like that guy right there. You can see, if you look hard, there's 1, 2, 3, 4. And they're all these particular angles. That's because, and so each one of those has the same thing. So pick the different one in here, like that guy, 1, 2, 3, and then there's one you can't see back there. So each one of them shares 1 electron. And that's good because Pauli exclusion principle. So each one of those little bonds in there has 1 electron coming from 1 carbon and 1 coming from the other. So they go into a 1 up, 1 down state. They're in the same spatial state. And then 1 up, 1 spin up, 1 spin down, which notably makes it not have any net spin. So no net magnetism here. This is a non-magnetic material. Both silicon and diamond are completely non-magnetic because I have 1 spin up, 1 spin down. We're not talking about nuclei here. You can have nuclear magnetism in any of these, depending on your isotope. But when we talk about magnetism, it is not about nuclei. The nuclear magnetic moment is much too small to be measured by other than pretty high precision techniques. Things that stick to walls, stick to your refrigerator, that's all about electrons, not about nuclei. Okay, so there could be nuclei in here. In fact, there certainly are. There's some will be carbon 12, some, et cetera, but it doesn't matter for this. Okay, so we call that sp3 bonding. And the reason we call that sp3 bonding is there is 1 s there is the way you might say 1 s and 1 s, there should be 2 s's and 2 p's. That's where I am in the periodic table. It should be 2 s's and 2 p's. But those levels at the hydrogen level are all degenerate with each other. So I can almost pick any of them. And if you really stop and think about this, you're going to get pretty confused because none of this is a hydrogen atom. So everything you learned about sp and what's degenerate and all your, how many of you have had a quantum class yet? You're in it now. Okay. So have you hit the hydrogen atom yet? Okay. So everything all the language I'm using, all the language that everybody uses is the hydrogen atom. And then when we take like anything else, carbon, silicon, we use the same language. And somewhere in here, I hope you get really confused by that because it is a bizarre thing that we can do that. And when you do get confused, ask the instructor. You'll get lots of points for asking a really deep question because it is a really deep question why we get to keep calling them S's and P's when, like silicon, I forget how many electrons, a lot of them. And why aren't they interacting with each other? And why do I still get to use any of the name nomenclature that I learned for the hydrogen atom? So, but we're not, you can ask me later if you want, but for right now, just let's slide on past that. Anyway, the point is sp3 bonding is really all about the nature. You mix together S states and P states to get a whole new set of states. That's the bottom line. They're just called SP, but they actually are new states. So sp3 bonding is what you get in diamond. sp2 bonding is what you get in graphite. And sp2 bonding is because you take two S states and two P states and mix those. Here you take one S state, three P states and mix those. So that's a lot of words. I mention it because the fact is that graphite and diamond have quite different bonding. And that will be true even when it's amorphous. So I can take a carbon, make it not crystalline, and depending whether I make amorphous carbon, depending on whether I make it mostly sp2 or mostly sp3, I will get really different properties, really, really different. So mostly sp2 will be soft and like, rub off in your fingers and look like, dirt. Mostly sp3 is something that is called tetrahedral amorphous carbon. It is not crystalline, but it is incredibly hard. It is about as hard, really good tetrahedral amorphous carbon is as hard as diamond. But I've made it by a thin film process, so I can use it for coating lots of materials. It's a big industrial product. So the reason I went into all that is the bonding in the amorphous materials, it's the same atoms. So in a sense, they want to be bonded the same way as they would be in a crystalline structure. And the properties sort of reflect that. So amorphous sp2 bonded carbon is soft and squishy and would not be useful at all for coating. Mostly sp3 carbon in the amorphous state is really hard and is really useful. And this whole industries in Silicon Valley that work on making this tetrahedral amorphous carbon. Not trivial to make it, but it can be done. So the bonding is not that dissimilar. So, okay, so at this point I've convinced you. Let's go back up a little bit. Okay, so two different things. Now, let's jump in. So this is an example of a crystal. Okay, so there is a typical crystal. That happens to be the face-centered cubic crystal. Lots and lots and lots of materials are in the face-centered cubic structure, like copper, gold, silver, platinum, lots of others, but lots of materials are in that structure. It turns out that if you have a structure like that, there are theoretical constructs that were developed like 100 years ago for how to talk about the electrons. So I'm mainly interested here in the electrons, although as I said, I'm talking a lot about structures too. But it is not trivial, and in fact, you already should know this. I'm not going to try and teach a condensed matter physics class right now, but in a given, let's call it 1 cubic centimeter of, call it copper, 1 cubic centimeter, or it doesn't really matter, it could be silicon, but let's say copper. So 1 cubic centimeter of copper, there are 10 to the 23rd atoms. That's a lot of atoms. Each of those atoms of copper has, I think, 29 electrons. All right. How many people in this room think that you can solve exactly something that has, 29 times 10 to the 23 particles in there? Yeah, keep your hand down if you started to say yes. I didn't see anybody saying yes, but trust me, you can't. We can solve one body problems. We can solve two body problems. We can solve three body problems sometimes. When I say solve, I mean in all generality. We can always stick things into a computer, tell it all of the initial conditions, and let it evolve. Although quantum mechanics even makes it that hard. At any rate, we're up to 3. Maybe 4 in some circumstances. That is a really long way from 10 to the 23. we can't solve the 10 to the 23 body problem. Like, it's not even close. It's not even, I mean, you're not, it's not even just a little bit impossible. It is completely impossible, except that it isn't. Because in things like this, with all of this symmetry and all of the periodicity, and some particular thing has happened to you with the Pauli exclusion principle for electrons, where they can't be in the same state. Again, I'm not going to teach you an entire solid state physics class, but the end result is you kind of can. You make some approximations, and those approximations turn out to be really good. So copper was a really good example, because even though this 10 to the 23rd, and I'm not going to worry about the 29 electrons, because it turns out the only one that matters, there's only one that matters, the outermost electron. All the others are kind of in fixed states that don't change, whether there's like 10 to the 23 atoms or just one atom. So most of the electrons are just in the same state they always were. But that outermost one, which is what makes copper be a really good metal, delocalizes is the word you should use. So that outermost electron delocalizes and can move around, and that makes copper a really, really good electrical conductor. Also makes it a pretty good thermal conductor. This all depends on something that we call a block wave description. So instead of trying to solve the 10 to the 23rd body problem, I can replace it with an equivalent one body problem because of the periodicity. And that is something called Fermi liquid theory, Fermi gas theories. When you start taking condensed matter classes, you will learn these things. Fermi gas theory, Fermi liquid theory, these are all words that are used to describe how you solve what is underlying an insanely complicated problem. Turns out not to be so complicated. But you do end up with some funny things, like the mass of the electron is not exactly the mass of the electron. It's usually like sort of a tenth of it. Sometimes it's 100 times larger, sometimes it's 10 times smaller. Weird things happen in this, what's called renormalization. Anyway, out of all of that, we have a pretty good model for how to describe copper. Turns out we also have a pretty good model for how to describe things like salt, NaCl, because NaCl is just one electron moves over to the other, and then you're kind of done with the problem. There's like, you're not really solving it. I want to generalize that statement just a little bit. The reason this all works actually is, at least in the metal part, the Pauli exclusion principle. I have to keep putting electrons. They may not be, I may not quite know the right wave function for them, but I do know they have to be in distinct states. So one thing I know for sure about electrons, they cannot be in the same state. So it turns out once you're done accommodating all of that, you get one electron for every copper. They have to be in distinct states. Those distinct states are different kinetic energy states. So when you're all done with this, the kinetic energy of the last electron that you just decide to calculate, turns out that's up at like EV, electron volts, which is that's like 10,000 Kelvin. So it's effectively at really high energy or really high temperature. And it turns out that kinetic energy is so much larger than any of the potential energy interactions that you can work on a kinetic energy. That's the heart of the approximation. You had a kinetic energy dominated limit, allows you to do lots of perturbation theory. So this is great. Allows you to describe lots and lots of things, really lots of things. Certainly how copper works, how sodium chloride works, how silicon works, pretty much everything, not quite everything. But my point is, it works pretty well, as long as you have that nice crystalline structure. But now, we're going to take away the crystalline structure. So I have shown something that I don't even believe in. This is just a blobby mess of atoms, and so that was the amorphous structure. That blobby mess of atoms does not have the periodicity, does not have the symmetries, doesn't have any of those things. Lots of short-range order, but none of the symmetries and global properties. So that means that, for example, momentum is not conserved. Energy, it turns out, is still conserved. So some things you can port over, but a whole lot of it you can't. And so that's where most of my colleagues, most condensed matter physicists, just throw up their hands and say, too complicated, we don't know what to do, so we're just going to ignore it. Which is interesting, but I'm not a theorist, I'm an experimentalist, so I'm a little more pragmatic about this. Because what I notice is that may be true, that I don't really know how to write down a precise theory, and yet, pretty much every property that I want to describe exists in amorphous materials. So there are amorphous metals, there are amorphous insulators, there's amorphous semiconductors, there's amorphous superconductors, ferromagnets, et cetera, et cetera, et cetera. So, but I'm kind of stuck now because I don't have this nice, simple model. So that's not quite fair. There are things we can do, and that's where we are right now, is trying to expand our tool set. And to motivate this, I'm going to give you a simple but very interesting example. Everybody in the room know what superconductivity is? Anybody not know what superconductivity is? Okay, everybody knows superconductivity. Okay, well, superconductivity was discovered over a century ago now, well over a century ago now. The theory for it was described in the 50s. It's called Bardeen-Cooper-Schrieffer BCS theory. And BCS theory, those of you guys haven't gotten there yet in quantum, right? Okay. So superconductivity theory is often described as an electron passes through that crystalline structure, going in this direction, and the lattice, just because it's a negative charge, so the ions around it all sort of pull in a little bit, this negative charge attracting the positive ions. Does that make sense to everyone? So they sort of shrink in. That means that another electron coming through the other direction is going to be attracted to that area, and it's going to pass through the same area, and that is the pairing mechanism. So put formally, they exchange a phonon. So phonon is a lattice, is a vibration of the lattice. This is not a real phonon is what carries heat and stuff in materials. This is a virtual phonon. So one electron, gives off a virtual phonon and the other one absorbs it. And that turns out to make an attraction. Further twist on that is now you actually make them into what's called a Cooper pair, but you can't put two electrons into the exact same state. Yet you just put them, I just said plus K and minus K. So they're in there. So I've got an oppositely directed, but they are in a single state. So the only way I can do that is with one spin up and one spin down. So a Cooper pair, that's what it is. It's one spin up, one spin down, plus minus K space pairing. That's fine, except for it totally relied on the crystal structure, because in an amorphous material, that electron is scattering off every atom. So you can't think of one going this way and one going that way. That doesn't even mean anything. So what theorists end up talking about is superconductivity is a really truly remarkable phenomenon. It's what's called, in many people's language, an emergent phenomena. It doesn't care about the underlying, really doesn't give a hoot about quarks at all. They just do not matter. You don't have to worry about those degrees of freedom. But you can extend that and really say it doesn't really depend on the underlying structure even. So the language that the theorists like to use is superconductivity is robust to disorder. So, okay, BCS theory, not quite right, but we're not going to worry about that because it's robust to disorder. So it survives being made amorphous, which it does. There are amorphous superconductors. So that's kind of cool, because in an amorphous superconductor, in the normal state, in the non-superconducting state above its TC, the electrons scattered like every angstrom. It's kind of the distance between atoms. So an electron scattered every angstrom. The mean free path was 1 angstrom. But it goes into the superconducting state, and now they can travel, it's the lifetime of universe. They can carry a current with no voltage. They never scatter. So it's a truly remarkable phenomena, but it's even more remarkable in the amorphous state, where they were scattering every angstrom and now they're not scattering at all. So the first statement is that is kind of amazing and even more emergent phenomena. But I would suggest that the more important statement, almost everybody in my field knows that, robust to disorder. So superconductivity, it's fine to have superconductors in amorphous materials. What they don't pay attention to is that there are many, many materials where the amorphous state, the TC, is higher than in the crystalline state, like significantly, like 10 times higher. So, my colleagues, the idea of robust to disorder, I just would suggest that doesn't really do justice to the fact that the TC can go up by a factor of 10. This isn't just robust to disorder. The disorder has actually enhanced the superconductivity by a lot. And that's the place where, most theorists that I know, most of my colleagues just don't know what to do with that. They're just like, yeah, well, this amorphous materials, I don't even want to think about it. I would suggest that by understanding that property, we have understood superconductivity much better. The fact that it doesn't require this crystalline state means we have to rethink BCS theory, and that was done. Person won the Nobel Prize, Phil Anderson, more or less for this. People often phrase it differently, but it more or less was this realization. It's not these plus minus K states. You can actually take one electron and think of it going scatter, 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 scatter. And now you can take a time reversed electron, which means it's going back through that same path. And as long as there was no inelastic scattering event, as long as energy, which means you just have to be at low temperatures, which you are anyway, it can go back through the same path, just like light can pass through an arbitrarily large number of mirrors, and you can retrace. You know, if you can get a light to go all the way through some complicated set of mirrors, you can go to the far side and go backwards, and a light reversed will go back through it. Same idea. So an electron scatter, 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 send it the time reversed electron, it will go back through the same reversed path. That's the pair. That is my Cooper pair. So it is time reverse states, not plus minus K states. There's also an important additional note, which is that disordered superconductors not only have higher TC, they are actually much better superconductors in the sense of practical stuff. They have type 2 superconductivity is almost all about disorder, where you have high critical currents and high critical fields. So all of the practical superconductors, that disorder is actually helpful. So again, my point is, it is somewhat like, okay, well, so maybe statement one that I need everything to be crystalline isn't true. So then statement two is, well, but disorder doesn't really matter, so I'm not going to worry about it. And I'm going to say that's not true either. Disorder helps. In many, many cases, disorder helps. Okay, so let's keep going with this. So often very flat and smooth, and this is important for technology purposes. This is a multi-layer made in my lab with a kind of a complicated multi-layered structure, which has tantalum on the bottom, and then amorphous terbium, gadolinium, and terbium, gadolinium are those rare earth elements down at the bottom. They have really big magnetic moments. Terbium X, gadolinium 1 minus X, cobalt 1 minus Y. That turns out to be a really good magnetic material. Those rare earth transition metal alloys are really good magnetic materials. And then platinum on the top. And the interesting thing, and the reason I show this for two reasons. One is it's really flat. So there's a lot of technology purposes like mirrors and things like that, where that is a good thing to be really, really flat. But the other thing is, look at X, I have X and Y in there. By varying X and by varying Y and by changing the growth temperature, changing annealing, I can make properties here be completely tunable. I'm not stuck with, when you make a crystalline material, you're usually stuck with an exact composition. And there's not that much you can do. Here, I have complete control of every property of magnetism within that one sort of set of materials. So that's just an interesting fact about amorphous materials. Now, I'm just going to skip ahead and just make a few more points. So in my lab, we have spent a lot of time studying amorphous silicon. It's not SiO2, it's just Si. It's a single element. There's its crystal structure. I've already shown you, it's a diamond. There is a model of the amorphous structure. The interesting thing about that, if you've looked at it hard enough, you'll see what happens is that every silicon in there is still fourfold coordinated and is still in a tetrahedral bond. So making it amorphous, it's lost its long range order, but it has not lost its short range order at all. Like the short range order is as strong in there as it is in the crystalline one. The bond length is the same, the bond angles are the same. There's a little bit of disorder in the bond angles, and I will just show you that briefly. So we've done lots of, this is literally, I've been working on this material for like, more than probably 15 years. You can vary a lot. You can vary the thickness, you can vary the growth temperature, you can vary the growth rate, and you get all different versions of amorphous silicon. These are sort of TEM pictures. We've done a ton of work on this. This is a long list of characterizations we've done, which I just show up. I don't know. We've done lots of work on this material. The thing I wanted to show you was this bond angle thing. So what happens is 109.5 is the tetrahedral bond angle. This is a plot of bond angle, the deviation from 109.5. It's actually the full width half max as a function of growth temperature. So as I grow amorphous silicon at different substrate temperatures, what happens is I get the bond angle very systematically goes down. So higher temperature makes me have a more ordered structure. Higher temperature, less bond angle disorder. But look at the numbers. 10. That's a full width half mass. So it's 109.5. The so-called bad amorphous silicon that I make at room temperature is 109.5 plus or minus 5 degrees. It's a very small amount of deviation from that 109.5. Really good amorphous silicon, which I make up here, is plus or minus 4 degrees. So it's very systematic, but it is a very small deviation. Like it basically is almost the same angle, but not quite. So we can study things like sound velocity. Those of you who know what phonons are, how many people know what a phonon is? Okay, phonons are vibrations. They do have a sound velocity. Yes, question. Bond length varies even less. So the bond length, I mean, they really, the atom is unchanged. So the bond length you can study through a plasma, plasma resonance experiment, and it's really hasn't changed at all. So the bond length varies less than the bond angle, and the bond angle doesn't vary very much. Okay, so we do lots of characterizations. Okay, this is really the heart of where I want to go, which is something called the energy landscape. And I want you to start, don't worry about the left yet, we'll start with the right. This is an energy landscape. Anybody who has, if you've looked at proteins, have you had talks on proteins or protein folding yet? No, okay. If you get a talk on protein folding, you will see this energy landscape idea is very pervasive. So what is it? This is, you'll see potential energies on the right. Remember I told you at the beginning, it's one of the reasons I stressed it so much, that I can make carbon in 2 different forms and they have different energies. Those different energies would be reflected on this energy landscape. So I have here, just let's start with the easy one, something I've labeled a crystal. I make a crystal out of something and I measure its binding energy. And when I say measured, that can be measured. You can measure the binding energy or the energy to take it all apart. That would lead to one dot here. That is one. So the bottom axis, which is labeled Z, is called the configuration, which is a little arbitrary, but I'll come back to what, but it's basically different configurations of the same number of atoms. So the crystal is one configuration and it has an energy. I made a crystal with a different, like my diamond versus graphite. I could have another crystal, it would have a slightly higher. So that's that one. Let's not, don't look at the ideal glass yet. Then I'm going to make all the rest of that is all about all the different amorphous states that I can make. So I take a whole bunch of atoms, and this is literally from a computer simulation of atoms where you can actually do this. It's harder to do it in the laboratory, the rest of this, but in a computer you can totally do it. Take a whole bunch of atoms, you actually liquefy them, you do that liquid quenching thing more or less. So you liquefy them in the computer, then you crunch it down and then you anneal it a bit to get it to kind of find local minima, and then you calculate its binding energy. And then you pick that configuration, you call it, you put it somewhere on the Z-axis on the bottom, and you put a dot where its energy is. And then what you do, what Z is reflecting is things that are near each other, like they're not that much different than each other, you put near each other on Z. This is actually a completely multidimensional space, which is a lot I'm going to show. And what you get is this crazy looking energy landscape, okay, which reflects all the different amorphous materials you can make and any crystals you want to put on there. So now, up high, when you have lots, so this does not show temperature on it, but if you are at high temperature, you basically sample all of it. So you're up here, skating around at high temperature. Then you start cooling down and you start getting lower and lower in here. And what happens is, and this is the glass transition, at some point you get trapped. So as you're cooling down, you get to, so when you get to here, you're going to get stuck here or one of those. But you'll still sample all these. As you go lower and lower, you get more and more trapped into some state. This is relevant to both the glass transition and protein folding and things like spin glasses where you get trapped in not the ground state. So the big question, if you're doing any of those examples I just gave, how do you get to the ground state? You can't. I mean, you can try and cool slowly and let it sample longer, but you're going to get stuck eventually. Now, I want to mention the entropy thing, which is over here on the left. So at high temperatures, you have, remember that entropy has something to do with the number of states. It also is a thermodynamic quantity, but let's start with the number of states. So at high temperatures, you have lots of, that's basically up here with lots of entropy. I start cooling, that's the liquid state. So I'm sampling everything. I start cooling down, and when you get to that temperature is where I usually freeze. When I get to that temperature, that vertical line there is the usual crystallization, where you go through a first order phase transition and you drop discontinuously with a change in it. So if those of you who remember a little thermodynamics, first order phase transition, Gibbs free energies are equal, but you have a change in S. And so this is that drop. If you crystallize, so then the crystal's down here. If you don't crystallize, which is the glass transition, you continue into the supercooled liquid state. So that viscousy glass that we started by talking about, that is a supercooled liquid. That's what you mean. You're actually below the freezing temperature, but for various reasons, SiO2 doesn't like to find the crystal structure. So it becomes this supercooled liquid. Supercooled liquid, everything about the supercooled, it is effective, well, not, it is a liquid still. It's just getting more and more viscous liquid, but it is a liquid. So it is still in equilibrium, and I can still talk about entropy and enthalpy, meaning all the way along here, it's reversible. So I follow the supercooled liquid line down with less and less and less entropy, which makes sense. There's fewer and fewer states lined up with it. So my concept of entropy is still fine. And as long as I stay in the supercooled liquid, that's a perfectly valid concept. But look at what happens when you get to low temperatures. Now I want to talk about that ideal glass, and that's really the last concept I want to do here. One short other one, but that ideal glass state is unique. And that's the place that, so if I tell you there is a unique state, what is the entropy of a unique state? Well, how many states are there? One. Entropy is the logarithm of the number of states. So how much entropy is there in the crystal? None. This is configurational entropy. How much entropy is there in this ideal glass? None. That's where most condensed matter physicists, they hate that idea, because to most people, they think of something that is disordered. They think of disorder equaling entropy. And the point is that's not right. It's not that disorder equals entropy. The number of states equals entropy. So what is that ideal glass state? Well, it's the state that has a ton of short range order. It's the state I've just been describing in silicon. So, and you can, so now I want to, that's the number of states version of this. The other thing you can do, you can measure the entropy also here. And now I'm talking experimentally. You can actually you can measure the entropy by measuring the heat capacity and integrating it. You can get to about here, and then you fall out of equilibrium, and then we have to stop talking about entropy. But you're not very far away, and in some materials you can get really close. You can extrapolate that thermodynamic entropy and reach the same conclusion, that there is, if you could keep it stay in equilibrium, you would hit this, you would cross. There would be just as low entropy in the glassy state as in the crystalline state. All right, so that is sort of, most theorists at this point there, that's what I mean by hidden order. It looks disordered, but it isn't. I mean, it looks disordered, but it is a unique state. It doesn't matter. Of course, I can rotate it, but I could do that with a crystal too. That's not the point. You know, overall rotations or translations don't matter. So the last thing I want to say about this, we access this, you will never get there by liquid quenching, but vapor deposition has this unique feature that I have a lot of surface mobility, so the atoms can land and still move around, even though I'm at moderately low temperature. So I can be below the glass transition temperature and yet still reach equilibrium. So there's increasing evidence that we can access this ideal glass state by vapor deposition. We see it in our amorphous silicon. We're looking for other inorganic materials. There's people out there working on polymers, and they've seen it. And the other unique thing I want to say about this is there is a particular property which is important. I guess I'll show it here. Sorry, one more. There's a property which has to do with, it's something called tunneling states, but it leads to dissipation at low temperatures. It leads to decoherence of qubits. that is all about amorphous materials. It also is directly related to what's called thermal noise in the coatings that are used for LIGO. So the thing when I've made this ideal glass, it doesn't have this dissipation mechanism. So the other slide I wanted to show you is that. So I wanted to point out, if I get trapped up here, I have other nearby states that I can jump to or tunnel to, and that's a dissipation mechanism at low temperatures. But this ideal glass state has no nearby states. So I've wiped out a dissipation mechanism, and that is directly relevant to qubits that need to use amorphous materials because they are what grow in many cases. So it's relevant to qubits. And so we believe that we've managed to make amorphous silicon that does not have this loss mechanism. And we're looking now to extend that to other materials. So, and that's the last thing I'll do. So what I want to say is that LIGO, which I'm not, hopefully you all know what LIGO is, but the mirror coatings, hopefully you all appreciate how insane it is, the detection that they're able to measure, what they do measure. But the detection relies on these mirrors and a laser interference pattern. And the leading source of noise at this point, because everything else has gotten better, is what are called thermodynamic mirror surface fluctuations, little fluctuations of the surface that leads to loss mechanisms. And that is something that we are making go away by making better amorphous materials, we can make those go away. And so we're hoping that we're successfully going to make the next LIGO mirror coating. So that's us. And then let me just conclude. So what I cut out the whole part because we really ran out of time, but there was a whole chunk I wanted to show you. I told you I was mostly working on electronic properties, and then I entirely showed you structural properties. But one of our goals, I talked to you about the superconductivity example. That's an old example, that's not mine. We are looking at other electronic properties, such as topological properties of electrons, and we have found them in amorphous materials, which again, many of my colleagues think is not possible, but we've shown it is possible. We've shown it's possible experimentally and theoretically. And so we're hoping by that means to force an extension. It's not that the theory is wrong, it's just that it needs to be extended. It needs to broaden itself to include the fact that disorder is not just not bad, it can be good. So that's the end. So amorphous system allows us to find these new phenomena, and theories rely heavily on the crystalline structure, but we're trying to generalize those. And then this whole idea of the ideal glass. So thank you for your attention.
Few minutes for questions. Are there any questions for the speaker?
I'm easily reachable by email too. So if you think of questions later, you're welcome to send me an email.
Have you found an experiment where your theory doesn't match what you're observing experimentally with the amorphous materials?
We have found, so I was, the best answer to your question is we found amorphous silicon has proven to be this just amazing material where we've been able to make it better and better and better, and fewer of these dissipation mechanisms. And we're even managing to make it lower and lower optical absorption, which is a slightly even more complicated property in a way. But that's all about one material. And there's evidence in polymers that the same sort of thing is happening, but they don't have the same, they can't do this. It's not about absorption. It's not about mechanical loss. So it's kind of a different set of things they're measuring, but enough related that it looks promising. So what I would say is it is proven harder than I thought it was going to be to find a second material. Amorphous silicon is amazing. But our whole approach where we think we're making this ideal glass in amorphous silicon, it seemed like we should be able to make it in other materials and the same thing would happen. And that may still be true, but we're not able to make it. So there's a way in which that energy diagram that I showed, it seems like that should be completely generalizable, but it's obviously not. So the best example I can give is we tried making SiO2 using these same techniques by raising the growth temperature and doing various other things like that. And what happened was we got all the properties to be better, but not orders of magnitude, not like so in that sense, we're right now trying to figure out, we think we understand why SiO2 doesn't show the things that we're looking for. And we think it's because we actually can't make the ideal glass there. So we need to have another material that we can make that has a similar energy landscape where we can make an ideal glass, and that's searching for that right now. So in that sense, we've definitely seen things that did not match what we expected to see. And I don't think we've disproven our hypothesis. I think we've just, there's just a lot of parallel paths out there. So we've shown, I still think the ideal glass is the right approach, but that it's harder to make the ideal glass than we knew. So I think I think that's, I don't know. I mean, you could ask Soren the same question. He's busy making, there are things we make that they don't, the world. The best description of this, I would say, is to refer back to your classes. When you take a class and you get a homework problem or you get an exam problem, there is an answer. And there is only one answer in a well-written problem. There's only one answer, and if you've been studying hard, you should be able to find it, unless the professor has written a bad problem. But in the real world, experiments, you can ask what is more or less not quite the right question. And then you have to rethink what you're doing. And so the real world is more complicated than classes are. I don't know if that kind of is, so you do things and they don't come out the way you think they're going to. And then you have to step back and say, okay, I don't think I was wrong, but it's like I'm off in a different part of the phase space. And I have to figure out now what's the new constraint.
Have there been any problems that you've been pleasantly surprised by?
Well, the first one we found, so the superconductivity is a really, that's not my example, that's last century. The topological insulator, was I surprised? Not really. There was a theory paper, I've been maybe too disrespectful of theorists. There was a theory paper that suggested this should be possible. And so I had a student that I showed this theory paper to, and then he decided to try and make it. And it kind of all just worked, which is amazing. Things like they don't usually work that well or that easily. So that we have one example right now of that side of things. And I would say offhand that so far the theorists are busy trying to argue with it rather than saying, okay, we need to generalize the theory. Some theorists are. We work quite closely with a person up at LBNL who this is what she does, is she's trying to figure out how to update the theory of topological insulators. And right now, I don't know, you should ask someone what he's working on, because right now we're trying to find, there's another property, well, rather generally, antiferromagnetism, where you have, one up, one down. And you can imagine where disorder would be a problem for that. Because if you have one up, one down, what happens when you have a triangle? Like, that's not going to work. So you're going to have one up, one down, and then what does the third one do? So it works fine if you have squares. It does not work well if you have triangles. And lots of materials make triangles. So in an amorphous material, you're going to probably have a mix of triangles and squares. So that's a problem for the amorphous state. But the thing that, well, Soren and I have been talking a lot about is, can we preserve what's called a bipartite lattice? Can we make a material where it doesn't have triangles, just does not have triangles in it? Again, local order is preserved. So can we make a material where it really wants to have squares? And then we should be able to make an amorphous antiferromagnet. So that's kind of, that's the world of experimentation. A lot of things you try, and sometimes they work out exactly the way you hope they would, and a lot of times you have to revise your theory. Or think again about a theory.
We're technically at the end of our room reservation, so maybe any further questions, please feel free to go up and ask them here. And also please remember to, if you haven't already, to use the sign-in form before you leave. It helps us keep the lectures going. There's also a slot there for emailing any questions to the speaker if you think of them.
I'm really easy to find too.
Yeah.
One thing, Soren, so you can always ask him, but if you can, it's fhellman@berkeley.edu, so it's about as easy as you can get.
Yeah, so happy Friday, happy Halloween, thanks everyone for coming.